Okay, guys, we're going to do some notes on free body diagrams. If you go ahead to the agenda, there are a few things that I want you to make sure that you get turned in today. So by the end of the period, you need to turn in the remainder of the concept organizer, which will fill in. So you may want to open that up that we were working on yesterday. Fill in the things that are missing, so have that on a separate tab. And then there are some notes on free body diagrams. When you're completely finished, spelling error. When you're completely finished, we're going to do some aviaries. I think I told a couple classes about that. So make sure you submit all three of those things. So open up your free body diagrams thing, fill in. I think we were missing a lot with frictional forces and air resistance, which we'll fill in now. Just pop back and forth between the two things or fill it in whenever you're finished. But the main thing that I want you to go through is the free body diagrams notes. You do need to hit turn in whenever you're done with those. So just fill them out as we go. Or if you like to take notes by hand, you can just pause the video whenever you need to and take notes and take pictures of your notes, turn them in at the end. Okay, so we talked about yesterday the Newton's 3 laws. We talked about free body diagrams a little bit anyways. So let's go into some more detail about free body diagrams. So just like we're taking notes in class, go ahead and open this up and let's take some notes together. Get myself out of the way here. I don't know where it put me. Okay, so Newton's second law deals with free body diagrams because we deal with the F equals ma thing. So free body diagrams look like this. This is just one example of what a free body diagram is. We can have 4 different forces acting on it. Most of the time, instead of this, I'll just draw it as a dot instead of a box like that. And then I have the arrows on it. I don't usually get into this much detail like normal force, applied force, gravitational force. I'll just put a sub G, sub F if it's a force of friction. So free body diagrams are used to show the relative magnitude and direction of all forces acting on a body. This diagram shows 4 forces acting on it. Obviously, we have the normal force going up, the force of gravity downward. We don't have to have those 2 things, although gravity doesn't disappear on the Earth. Applied force and frictional force, again, those don't have to be there. We could be missing an applied force. Maybe only the force of friction is acting on an object. There can be 1 force if an object is just falling through the air and there's no air resistance on it. There can be 2 forces, 3 forces, or all 4. We could even have 5 forces. Maybe we had normal force and then there was a rope attached also, so there was a force of tension on here. All of those things are possibilities. So let's do some examples. Let's draw an example of a book at rest on the tabletop. So think about your book or your Chromebook that's sitting on the tabletop. We draw a dot as the object, and then we draw all the forces that we can think of that are acting on it. So when an object is sitting, like a book on a desk, what do we see as, or what do we think of as forces acting on it? Well, we have the force of gravity, of course, because gravity doesn't disappear. It's always acting on an object, but then the table is still pushing on that object as well. So we have the normal force upward. Now, if the book is just sitting at rest on the tabletop, there's no other applied forces. Remember, we said if the net force is equal to 0, it's either sitting still or it's traveling at a constant velocity. So if we have a book that's sitting still right now, those 2 arrows should be the same size. So hopefully you drew this arrow and this arrow the same size. One should not be bigger than the other, because if one was bigger than the other, that would indicate that we had an overall net force of something other than 0. Anytime we draw a free body diagram, like we just did here, if we forget the fact that I drew those crazy things, a second thing always needs to be drawn, and that is a net force. So anytime you draw a free body diagram like this, you're always going to draw a second dot, and then you're going to put net force. Sometimes net force will be equal to some number, and we'll know what that is right away. Sometimes net force will just be an arrow indicating overall what direction is the object moving if we don't have numbers involved. Now, because we said the normal force and the force of gravity on a book that's sitting on the table are equal and opposite, the net force on this one is equal to 0. So if you know what that net force is, put it in. We know that the net force is equal to 0. And since we have that, there's no arrows involved in that. All right, so let's think about this one. An egg is free falling from a nest in a tree. We're going to pretend like there's no air. If an egg is falling from a nest, draw a free body diagram showing the forces that are involved in this. So again, we draw the object as a dot. So if we have an egg falling, there is the force of gravity pulling downward. We have the force of gravity, which does not disappear on the Earth. It's always pulling downward, force of gravity straight down. Now, if there's no air resistance, there's nothing opposing that force of gravity. So this is it. This is all we have that's acting on it. We don't have anything shoving the egg in a different direction. We just have gravity pulling it down. And like I said, with every free body diagram, we need a second dot that shows the net force. And in this particular case, since we don't have any numeric values, we can't put anything here. We don't know how many newtons that is, but we do know that the net force is the same as the force due to gravity because there's nothing opposing it. So net force is going to be the same as the force due to gravity in this particular example. We just can't put anything until they would give us some numbers. If they gave us the mass of the egg, then we could fill that in. A rightward force is applied to a book in order to move it across the desk with a constant velocity. Consider frictional forces and neglect air resistance. All right, so here we have our book. Now we're taking and we're pushing the book with a constant velocity. So we're applying a force. My hand never leaves the book. It's applying a force on the book, but we also have friction working against it. So let's just think about the basics in the vertical direction. We have the force of gravity that doesn't disappear, and the table pushing back up on the book, that's the normal force. Those two things should be equal and opposite to each other. Then we're applying a force. So depending on what direction your object is moving in, let's say the object is moving to the right, our applied force would be to the right. Force applied. But then it says consider frictional forces. So the one thing that we care about is the fact that it's traveling at constant velocity. Remember the soccer ball yesterday? After my hand let go of it, it's different than this situation, but after my hand let go of it and I wasn't applying a force anymore, it traveled at a constant velocity down the hallway. So the forces in the x direction, in the horizontal direction on that soccer ball after I let go of it were equal to 0, and it was traveling at a constant velocity. So the same thing is in this particular situation. We have a constant velocity, so the x forces, the horizontal forces, need to be the same. So if I'm applying a force in one direction, there has to be an opposing, equal, and opposite force in the opposite direction, and that's where friction comes in. Frictional forces always oppose the direction of motion. So overall, my net force in the vertical direction, in the up and down direction, is 0. We have no net force in the y direction, excuse me if I said x. And we also, because the applied force and the frictional force cancel each other out, we have no net force in the x direction. So net force equals 0 newtons. So we have 0 net force on this in the y direction and in the x direction because they're equal and opposite. And we can still have a moving object just like we had the soccer ball at a constant velocity if the net force is equal to 0. It's not accelerating in any direction. It's traveling at a constant velocity. Okay, now we have a rightward force. It's telling us, did it tell us in the last one? Oh yeah, we said this. I overlooked that. A rightward force is applied to a book in order to accelerate it across the desk. Consider frictional forces. So we still have frictional forces, but now we're accelerating the object. And what that means is it's not traveling at a constant velocity. It's now going to be speeding up across the desk. So here's our book. We have the force of gravity downward. We have the normal force upward. Those should be equal and opposite because the book is not moving up or down. It's moving across the desk. We still have, because it's moving in the rightward direction, an applied force to the right. Well, we have frictional forces. And we have to think about how big is that frictional force arrow going to be. We know it's going to go to the left because frictional forces always oppose the direction of motion, but it's going to be smaller, right? Frictional force, if it was the same size as the applied force, we would have this situation, constant velocity. But instead now we have an object that's accelerating. So when I draw my net force, my second little diagram here, in the vertical direction, in the y direction, my normal force and my force of gravity are equal and opposite, so they cancel out. But in the x direction, in the horizontal, my frictional force is less than my applied force. So in this particular case, we have a net force that is to the right that is not equal to 0. And I like to put that, if you know it's not equal to 0 because you know the object is accelerating, then you can say it's not equal to 0, knowing that there's an overall net force in some direction making the object accelerate. Make sense? Okay, normal force on an inclined plane. We did draw this a little bit yesterday. The force of gravity points straight down toward the Earth. That's this. That's the weight of the object pointing straight down toward the Earth, right? It goes straight down. And the normal force is a force that's perpendicular to the surface. So the normal force in this particular situation is right here. It's perpendicular to the incline that the object is sitting on. So a couple of things about balanced and unbalanced forces. If the forces are balanced, no acceleration happens. So if we have a net force that is equal to 0 newtons, we have balanced forces, and there's no acceleration. However, we can be not moving, so the object is sitting still, or we can be traveling at a constant velocity, like the soccer ball down the hallway. So the object can be moving or not moving if the forces are balanced. It's traveling at a constant velocity or if it's sitting still. Anytime we have unbalanced forces, however, our net force is not equal to 0, and therefore there is acceleration that happens. The object is speeding up or slowing down. And that's when, like, if I took a book and I shoved it across the table, it would eventually slow down. This is what we were talking about with Newton's first law of motion, and how it's hard to conceptualize the second part of it, where objects that are moving want to stay moving. It's because most of the time the forces are unbalanced, or in every situation they're unbalanced, and eventually that object will accelerate to a stop. We know that's negative acceleration or deceleration. Okay, so let's do a little math with it. Keep an eye on the time. All right, so let's bring some numbers into it. This is simple. What is the net force on a ball with 30 newtons of gravity pulling down? So again, we're going to always draw a free body diagram before we get into too much. And if we know some things to label it as, force of gravity is pulling downward, and that's 30 newtons. We'll put the numbers into our diagram. And 10 newtons of air resistance pushing up. So again, since I know this is less, my air resistance is less than my force of gravity, I'm going to draw it that way to help myself. We're going to just put air. That is 10 newtons. Because if you see that one arrow is bigger than the other, then you know overall the net force, because we're going to draw our second thing. We know that because the smaller arrow, or the downward arrow, is larger than the upward arrow, we know overall we're going to have a net force of 20 newtons downward. So it says, what is the net force? Oh, we did it already. What is the net force on a ball with 90 newtons of gravity pulling down, 10 newtons of air resistance pushing up? Well, the overall resistance is 20 newtons downward. Remember, well, I don't know if I said this yet. I know we talked about it with acceleration. Forces have directions, obviously, because they're vectors. So 20 newtons is only a number. That's a scalar, and we need a direction with it. So we're going to say 20 newtons downward. If a rightward force of 160 newtons is applied to push a box with a mass of 40 kilograms across a frictionless surface, what horizontal acceleration is experienced by the box? All right, so now we're getting into solving some mathematics, which we shouldn't need a calculator for on this one. So draw a free body diagram to start with, okay? So we have all of the things happening. There's a box. Box has gravity pulling it down, so we have the force due to gravity. The box is sitting on a table, right? Obviously, it's sitting on a surface. It says a frictionless surface. Therefore, we have the normal force pushing upward. Force of gravity and normal force are going to be equal and opposite. They're going to be the same size because the box is only moving horizontally. It's not moving vertically. Or it's only accelerating horizontally. We apply a rightward force of 160 newtons to push the box. So to the right, we have a force applied, which is 160 newtons. What is the acceleration experienced by it? And it's frictionless, so we don't have any friction working in the opposite direction. So this is it. That's all we have going on. But remember, for every free body diagram, we need a second diagram showing the overall net force. Now, the vertical, force, gravity, and force, normally they cancel out, they're equal and opposite. But in this particular diagram, there is nothing to help cancel out the applied force. So our overall net force, force net, is equal to the same as the applied force, which was 160 newtons. All right. So now we know that the net force is equal to the applied force. If we had something else opposing it, then we would subtract that from it. Well, we don't. We don't have any frictional forces. So net force. Now, herein comes because obviously they give us another value and they want to know something different. What is the acceleration? So we're going to list our variables. We have acceleration as our question mark. We have mass as 40. What happened there? Mass as 40 kilograms. And we know the overall net force. Now, I'm not going to list my other forces because I'm going to tell you right now, anytime you have net force as an actual value, you pretty much have a part of the equation that really matters. So anytime you see net force, and we wrote this on the board, I believe the equation should still be up on the board as long as I didn't erase it. Net force, anytime you see net force is equal to ma. Net force is mass times acceleration. So right now we have everything we need. We're going to plug in our 160. We're going to plug in our mass of 40. We're going to solve for A. So this should be pretty easy, right? You can do this without much help. Your acceleration of the object is 4 meters per second squared. Now, because acceleration is also a vector, it has a direction. So you need to, I hope this is what they're asking for, the acceleration, yeah. You need to say 4 meters per second squared to the right. Or if you know that to the right is the positive direction and you keep that as a positive force, then that is acceptable as well. So you could just put 4 meters per second squared as long as I knew your initial net force was positive. Okay, let's try this one. If a rightward force of 160 newtons is applied to push a box with a mass of 40 kilograms across the surface and experience frictional force of 30 newtons, what horizontal acceleration is experienced by the box? So now instead of having a frictionless surface, now we have friction. So it's going to look very similar to our last one. We have gravity working down, force due to gravity. We have the normal force pushing up. They're equal and opposite. We have an applied force of the same value that we had before. Force applied is 160 newtons. Now we have friction opposing it. Really tiny, still small. It's not as big as our applied force. We have a force of friction of 30 newtons. All right, so our overall net force diagram is going to look a little different than this last one that we did. So in the vertical direction, force normal and force of gravity cancel out. But now in the horizontal direction, we have an applied force, but then we have an opposite frictional force. So we have an overall net force of 130 newtons. Force net is 130 newtons to the right, right? Because if we have 160 in one direction and we have 30 in the opposite direction, we just subtract them and we get 130 newtons. So now it looks a little bit different. Now we have our net force of 130 newtons. We have a mass of the same 40 kilograms, and they're asking what's the acceleration. Now, I'm going to ask you before you go on to actually solve this, do we expect the acceleration to be larger or smaller than what we just figured out? So think about, this is with no friction and how fast it accelerated. Do we expect this acceleration to be larger or smaller than 4 meters per second squared if we're introducing the idea of friction into the equation? So when you get your answer for this and you do the mathematics for this, you divide them out, right? Net force equals ma. So we get 130 equals 40 times a. Think about whether your answer makes sense when you get your answer. Does it make sense that if the acceleration is what you think it should be? Hopefully you can think in your head that you expect it to be smaller because obviously if we have friction involved, it's going to not accelerate quite as much because we have an opposing force to that motion, that applied force. And we end up getting something like 3.25 meters per second squared. So if you got a value that was something like above 4, like 5 meters per second squared, I crossed off my answer. You can think about that and think, well, that doesn't make sense because obviously it's not going to be larger. Okay, so let's talk very briefly about frictional forces because these are some things that you're going to add into your free body diagram that I want you to finish up. So friction is just a force, another kind of force. Let's see, is this in frictional forces? Yeah, we have some. Okay, friction is just a force that that is between two touching objects. It depends on the material that the object is made of and how bumpy the material is and what the substance is that it makes up of. So if you think about it, this is why our tires on our car are not made of something like plastic or steel. They're made of rubber because rubber has a different coefficient of what's called a coefficient of friction than something like a metal does or like plastic does. So if you're trying to slide, let's say, a box, if you're taking a box and you're trying to slide it across the carpet versus taking a box and sliding it across cement that's poured out or, the type of cement that's really rough, or a piece of sandpaper. Not that we have a giant piece of sandpaper we're trying to slide a crate across, but think about what the substances are made of. There's different things called coefficients of friction that dictate how much friction occurs between two surfaces. If we have surfaces that are more bumpy than others, we have different frictional forces that can exist. If the objects are pushed together more, so this is why if you have a pickup truck, why you load up the back of your pickup truck with sandbags in the wintertime, because if you have more pressure between the surfaces, then you have more frictional forces that exist. That's why light trucks with no weight in the bed of the truck slide around in the wintertime, is because there's no frictional forces or very little frictional forces. Friction is a force that affects motion. It acts on materials that are in contact with each other. Friction always opposes the motion, so friction's always working against the direction that the motion or the applied force is, almost always. When two solid objects come in contact, the friction is mainly due to irregularities in the two surfaces. That's why smooth surfaces slide past each other a lot easier than rough surfaces do. And it does not cause motion, it responds to motion. So friction only acts if there's motion happening. Friction is non-existent if there's not motion that's trying to happen. So the two types of friction that occur between objects are static friction and kinetic friction. I wanted to try and give this example. I'll do it with my calculator. So static friction and kinetic friction are different. Static friction is friction that is between two objects that are still and not moving. It's what holds an object in place and keeps it from sliding. And kinetic friction is the friction that exists when an object is moving. Static friction is generally higher than kinetic friction. So with your calculator, and I'm going to do this example with my calculator. So on one side of your calculator, right, you have your plastic keys. I don't know how to do this best. If I was here at class, this would be a lot easier. Okay, so I have my thing inclined, right? And I let go, right? If I let go, my calculator slides down the surface. But on the other side of my calculator, those little rubber gripped things, right? If I put that on the surface and I have it at the same incline, that it is being held in place by what's called static friction. Static friction is the friction that holds objects in place and keeps it wanting to stay there. Kinetic friction is the friction that exists after an object is moving, right? So I can have my calculator sitting this way, and as I slope the surface, there's not a lot of static friction that holds plastic and plastic together, but there's a lot of static friction between rubber, those little rubber pieces, and plastic. Now, static friction, the friction that holds an object in place and doesn't want to let it go, is generally a lot larger. Like this is really, really large, except for if we started moving the calculator. Once it gets moving, it's not really working, but it would work better if I had a desk and I was doing this in front of you. Just understand that static friction generally tends to be larger. Once you can get an object moving, it's a lot less difficult to keep it moving, to overcome friction, than it is to actually get it started in the first place, to get the object moving in the first place. So one last thing. This is the equation for calculating not only, think this is in your thing, the coefficient of kinetic friction and the coefficient of static friction. So this is the basic equation you can put under both of them. This little guy right here, this little thing called mu, is the coefficient of friction. That value changes depending on what the substances are made of. So if I was looking up that value for frictional forces for my calculator I just showed you, I would have to look up the value for plastic on plastic or rubber on plastic. So this value changes depending on the surfaces. Every pair of surfaces, you have a different coefficient of friction. And really that value can just change. Let me see if I have it in here. I guess this is a good example. This value changes depending on what the substance is. So coefficients of static friction are just mu sub s, and coefficients of kinetic friction are mu sub k. And you can see like rubber on dry concrete. So think about that when you're driving down the road in the summertime and the road is dry and your tires are spinning on the thing, spinning on the road. Static friction is a very large coefficient of friction versus kinetic friction. But look down here at the bottom, like your shoes on ice, even if they have rubber, or ice on ice. If you have a piece of ice on a piece of ice, it has a very small static friction and kinetic friction both, because those two objects, when they're rubbing together, do not have much friction that occurs between them. So depending on what the two objects are dictates how much friction occurs between those two objects. I want to say that should cover most of it except for terminal velocity, which we'll talk about falling objects another day when I get back. Okay, so at this point, what I want you to do is you will go ahead and turn in don't turn in these notes. I said to do that at the beginning. Actually, go ahead and hit submit. You'll open them up and submit it a second time. So go ahead and turn in these notes. The other thing that I need for you to do is to go and hopefully fill out the rest of your concept organizer. Hopefully you got that filled out as we went. And there it is. So there was a few things that you went. The only thing that you will have to fill in left is terminal velocity, which we'll cover that a lot with falling objects, so you can fill that in later on. And then if you go back to the agenda, today the last thing I need for you to do is go in and do aviaries, which I know you guys love. Aviary. Don't worry, these are a lot easier than normal. And there's one that's a little bit different than it normally is. So remember, what I need at the end of this is screenshots. There'll be two because there are two aviaries. Please make note of the fact that one of the aviaries is a little different than the other. The first aviary, you have to get it right. You just have to take a screenshot saying your answer is correct. The second aviary is a little different than normal. You have to get a score of at least 10 in order to turn it in. It starts out with a score of 0, and every time you get it wrong, it goes back to 0. You add a point every time you get one right. You'll understand once you go in. Once you get to 10 points, then you can take a screenshot. Make sure that your name is included in your screenshot, because if it's not, you're going to get a 0. If your name is not on there, you have to click somewhere on the screen and it will pop up with your name and your total score once you're done and you've reached a score of 10. Anything less than 10 will give you half credit. And if your name's not on it, you're going to get 0 credit. So there's only 2. Good luck on it, and I'll see you tomorrow.